everyone, this is Zhifu.
This is Chen.
This is Chuhan.
And today we are going to discuss our course project on eco-approach IoT car with signal optimization.
According to the trend of transportation and real-life demand, two major features of future vehicles should be smart and eco-friendly. Currently, people from all over the world share the same concern on environment condition. Over 23% of carbon emission was caused by fuel-powered vehicles since 2012. At the same time, the increasingly frequent huge traffic jams arose too many complaints on roads. The severe condition brings the smart electric cars into our attention. Electricity is a kind of much cleaner and more eco-friendly energy to power the cars, and we can even save more by optimizing the running track. Based on that, we want to design an algorithm to make cars running in a smart way to avoid traffic jams and too much energy consumption. To validate and elaborate our algorithm, we refer to papers about eco-friendly cars and research dealing with the influence factors for engine consumption and carbon emission. And we got some valuable information that emissions are related to vehicle type, its instantaneous speed and acceleration. And the relative large acceleration plays the major role in vehicle emission.
We are going to discuss the formulation of our IoT cars. The first picture is the top view of the IoT car. In the center, we could see the Raspberry Pi 3. It is the head of the car. It connects to various sensors and runs the algorithm accordingly. On the right of the Pi board is the A battery. It powers up the control board and the motor. In between is the L298N motor control board. It could receive PWM signals from the Raspberry Pi and let the motor run at a certain speed. There are 4 wheels and 1 motor for each. The motor could let the vehicle run. The picture on the left side is the front view of the IoT car. The ultrasonic sensor is in the front, and it will detect the distance to the board and then calculate the distance to the traffic light. In the bottom is the power button to power up the Raspberry Pi. There are 2 Hall effect speed sensors to sense the speed of the wheel, and we could use them to calculate the travel speed and distance. We use the built-in light on the hazard board to illustrate the traffic lights. Here, note that the blue light actually represents the green signal.
To reduce the gas emission. This is related to the velocity and acceleration. It could be observed that smaller velocity and acceleration are better. We could observe that the current velocity, the space height width, and the traffic schedule. Based on this information, the PWM could be used to change the spin speed of the motor. There are several constraints for a realistic scenario. First, the car should always stop when facing a red light. Second, cars shouldn't speed up to go through a light. Finally, it should avoid collision. Humans could just change their speed by current light status. However, an eco-approach car, it will always consider status when it's approaching the light to make it change more smooth. For example, it could predict the red light, so it could slow down earlier. With this low velocity, it doesn't need to stop when approaching the light. The framework for velocity control is the same for both kinds of cars. For the control system of the car, there are 2 levels. The high level is to calculate the next acceleration based on difference between the current velocity and the expected velocity. Then, lower control could use these parameters to calculate the next PWM.
Here's an illustration of our IoT car. On the top is the traditional human car, and on the bottom is our eco-approach car. We could see that when the car approaches to the light, the human car will make a sudden stop on the red light and then restart in the green signal. On the other hand, the eco-approach car decelerates in advance, even if the car is green now. It avoids making complete stop at the red light and thus generates less emission. Here is the data visualization. Note that in order to avoid outliers, we tested our car 10 times and obtained the data. The graph on the left is the acceleration versus time. From the graph, we could see that there are some outliers, and the car have a large acceleration when start and when passing the traffic light. The graph on the right is speed versus time. We could also find that the initial speed for human is relatively high, which means that it runs at the maximum allowed speed. When encounter the traffic light, it will go almost completely stop and then restart. The eco car could pass the traffic lights by optimizing its speed, and it doesn't need to do the complete stop while in red light and could keep its original speed. The second graph is the total emission versus time. We could find that the human control cars tend to generate more emissions and some sudden increases on the emissions. On the other hand, the eco cars tend to have less total emissions and less observations on subtle increases on the emissions. After qualitative analysis, we now move to the statistically analysis part to make sure that the result is statistically significant. Two simple t-tests is a standard technique to compare two groups of data and analyze whether the true means of the two groups is different or not. Through that, we could find that the average pass time on a certain distance is different at 5% level. On average, humans spend more time passing through the traffic light due to the complete stops. The average total emissions on a certain distance is different at 10% level, which means that on average, human-controlled cars generate 23% more energies.
From the experiments and data analysis above, we have drawn the conclusion that eco-approach cars, which communicate with IoT traffic lights in real time, perform better in energy saving and could generate light emission. However, our algorithm still suffers from some limitations when applied to the real-life cars, such as communication delay between the traffic lights and IoT cars. For the further step, we will aim at dealing with complicated situations, such as multiple traffic lights, more cars in different directions. Also, we will try to select better parameters with a large set of data and advanced data analysis methods. Here are some helpful references. Thanks for listening.